What if we told you the answer to the world's clean energy crisis has been sitting in our backyard this whole time? No, seriously. Buried in the earth is a silvery metal, 3 to 4 times more abundant than uranium, capable of fueling reactors for thousands of years without melting down, generating toxic waste, or breaking the bank. It's called thorium, and thanks to a group of Danish engineers, it's about to change the world. Back in the 1950s and 60s, U.S. nuclear pioneers envisioned a future where electricity would be too cheap to meter. Alvin Weinberg, director of the Oak Ridge National Laboratory, championed molten salt reactors running on thorium. His team ran a thorium reactor successfully for 15,000 hours. That's right, over 4 years of continuous operation, generating a stable 8 megawatts of heat. And that's enough to power a small town. But then came the budget cuts. The Atomic Energy Commission pivoted to reactors that were more compatible with nuclear weapons programs. Thorium was left in the dust, and Weinberg was fired for insisting on its promise. As he wrote in his memoir, The First Nuclear Era, 1994, "I hope that in a second nuclear era, the molten salt technology will be resurrected." Forget IKEA. Denmark's latest modular miracle comes in a steel box, a small modular thorium reactor the size of a shipping container. Copenhagen Atomics plans to mass-produce 1 reactor per day, delivering them in 40-foot containers and scaling nuclear power like never before. If you really want to have 10 or 20 or 100 times more energy on this planet, then we need what is called breeder reactors, says Thomas Jan Petersen, CEO of Copenhagen Atomics. Unlike uranium, which is just 0.7% fissile in its natural state, thorium is incredibly abundant, up to 500 times more effective when you consider usable nuclear potential. But here's the twist. Thorium isn't fissile on its own. It needs a neutron kickstart, and that kick comes from uranium-235 or plutonium-239. Once seated, thorium-232 absorbs a neutron, becoming thorium-233, which quickly decays to protactinium-233 and then to uranium-233, a fissile material. This kicks off a chain reaction that creates more fuel than it consumes. And as physicist Kirk Sorensen famously explained, you need 1 neutron to sustain the reaction, another to convert more thorium, and then you have a surplus neutron, creating fuel as you go. Thorium works best in a molten salt reactor, MSR. Unlike conventional reactors that use solid fuel rods, MSRs dissolve thorium and uranium directly into molten salt. The benefit? Continuous reprocessing. You can remove waste products while the reactor runs. Even better, MSRs operate at atmospheric pressure. No pressurized water. No steam explosions. If something goes wrong, the reactor safely shuts down on its own. The molten salt cools and solidifies, locking in radioactive materials. And the failsafe? A frozen salt plug at the base. If the reactor overheats, the plug melts, draining the salt into a secure tank. That's walkaway safety, folks. The onion core design. Copenhagen Atomics MSR sports an onion core, and here's how it works. The inner core, fuel salt flows through this region to generate heat. The middle layer, heavy water slows neutrons, making them more easily absorbed by thorium. The outer layer, a breeding blanket of thorium salt, absorbs stray neutrons to create uranium-233. And here's another mind-blowing fact. Thorium reactors can consume nuclear waste. The fissile starter material? It can be drawn from spent fuel from conventional uranium reactors. That means we could actually reduce the stockpiles of legacy nuclear waste while generating clean power. And the waste from thorium reactors? It decays in hundreds of years, not tens of thousands. Say goodbye to 100,000-year storage solutions. But one of the major hurdles has been the materials. Molten salt is hot, 700 degrees Celsius, and corrosive, and the reactor is under constant neutron bombardment. So, Copenhagen Atomics engineered custom alloys and a levitating molten salt pump, which uses magnetic bearings to avoid physical wear. They're running ethylene salt, fluoride, F, lithium, Li, sodium, Na, potassium, K, through testing loops to optimize everything, from sensors to pumps to heat exchangers. In 2026, Copenhagen Atomics plans to fire up a prototype at Switzerland's Paul Scherrer Institute, one of Europe's top nuclear research centers. It'll run at just 1% capacity, but it's the crucial first step to validate their computer models. Then, over the next 4 years, the team aims to begin transferring uranium-233 from the breeding blanket to the core, a key milestone toward full self-sufficiency. Global race to breeding power. But China isn't just watching. In October 2024, it ran its own molten salt reactor with thorium and uranium for 10 days at full power, breeding protactinium-233 in the process. In April 2025, they topped up the fuel without shutting down the reactor. Impressive, but not yet a full breeder reactor. No one has cracked that milestone yet. But Copenhagen Atomics is confident they can. Their projected energy cost? Just $20 to $40 per megawatt hour, mere fraction of today's nuclear rates. But here's the twist. Copenhagen Atomics won't sell you a reactor. They'll build it, run it, maintain it, and decommission it. Clients only pay for the heat or electricity. No nuclear expertise needed. Their first customer? Indonesia, where the reactors will generate clean energy to produce ammonia and hydrogen, two essential industrial ingredients. On the other hand, if we talk of solar and wind, they're great, but they can't produce the high heat needed for processes like paper drying, aluminum smelting, or fertilizer production. This makes thorium reactors not just an electricity solution, but an industrial revolution. Ironically, the biggest challenge isn't the tech, it's the red tape. Nuclear licenses and approvals are costly and time-consuming. But once the first 100 reactors are deployed, Peterson believes the process will streamline. Licensing is one of the most expensive parts of this, he says, but scale brings efficiency. Did you know? Thorium was discovered in 1828 and named after the Norse god Thor. 1 ton of thorium can produce as much energy as 200 tons of uranium or 3.5 million tons of coal. Unlike uranium reactors, thorium reactors produce no plutonium, a major proliferation advantage. With climate change accelerating and global energy demand soaring, the timing couldn't be better. We need clean, scalable, safe energy solutions now. And thorium delivers on all fronts: abundance, safety, cost, and sustainability. So, will thorium finally take center stage?